and let's talk about multi-level modeling. So, we have two basic types of multi-level models, and within each of these types, there are a number of categories of multi-level models. We're going to focus on just these two types today. The first type is the multi-level model of growth or change across time, and this model is actually we'll get to it. We're gonna look at this today. It's just an extension of latent growth curve modeling. The other type is kind of within cluster associations, where we have clusters as either subjects or clusters as clusters, and that might sound like a cluster, but we'll talk a little bit about what I mean. The clusters as clusters really has to do with the fact that multi-level modeling actually grew out of education and the examination of classrooms, students nested within classrooms, nested within schools, right? And so those are clusters within clusters, clusters of classrooms within clusters of schools, or clusters of students and clusters of classrooms and clusters of schools. And so we're going to talk a little bit about both of these types today. So as far as change goes, the multi-level model for examining change is really no different than a latent growth curve model, although it is more flexible than a latent growth curve model. In this example, you don't have to take notes. Obviously, the video is recording. You're gonna be good to go. In this model, it's if you imagine, instead of the latent growth curve model that we normally have, in the latent growth curve model, right, we get a slope of time, and we get an intercept, which is what? What is our intercept?
Average level of the variable
at any time point, right? Yeah, whatever time point is coded as zero. And the same thing applies in multi-level modeling. If you use time as your predictor, then you wind up having, and so just like if we look at this, in latent growth curve modeling, you're going to have participant 1, participant 2, participant 3, participant 4, right? Then you have time 1, time 2, time 3, time 4, and your data is structured like this, right? Like 3, 3, 4, 5, 5, 4, 5, 7, 6, 7, 9, 8. Let's get rid of time 4 just so I can be done writing. Right, and this is how your data is actually structured. This is person. And if you open an Excel data file, it would look something like this, right? In multi-level modeling, this is called, anybody know what kind of format this is called?
White.
It's called white format, yeah. Multi-level modeling, though, uses long format, which is different. So in long format, you're going to have person, right? And then you're going to have time, and then you're going to have score. And so you'll have time 1, 2, 3, 1, 2, 3, 1, 2, 3, person 1, person 2, person 3. I'm not going to draw person 4 up here. And then for scores, you're going to have 3, 5, 6, 3, 4, 7, 4, 5, 9. And just for simplicity's sake, I'm going to get rid of person 4 over here. And so you have your data structured like this, and this is called what format? Long. We have wide. And so latent growth curve model, you would have time 1, time 2, time 3. You'd have a slope, an intercept, 0, 1, 2, 1, 1, 1. Over here, it's just a straight regression equation, right? And the regression in this point is all at level 1. So we're going to have something like this within, and we would say like, we just call this slope line. This is how we actually type this into M+, just FYI. And we would say, let's not call this score. Let's call this V, whatever. V on T. Then you're going to have between, and then you'll just have S and technically V. And what you get here is the exact same thing that you're going to get over there, right? With a few exceptions. This is going to be your random variance component for your slope, your random variance component for your intercept. That's the same thing that we have right here. That's your, these would be your random variance components for your slope and your intercept. And then you'll get the effect of S is going to be represented up here. And it will make a little bit more sense when we do this, but you'll get a mean of S. Actually, it puts it down here. You'll get a mean of S, a mean score for S, and that's your, and a mean score for V too, I'm sorry. And that will be your slope and your intercept that you would have over on the other side, right? The mean scores of slope and intercept. So, the main difference between the two is that when we do growth curve modeling, and we'll test this today, and you guys will be able to see this, growth curve modeling gives you a random variance, or not a random variance, but an actual variance for each time point, right, across time, because you have 3 different variables, and so each observed variable can have a variance associated with it, right? However, with latent growth curve, with multi-level modeling, you don't have 3 variables that represent time, or I'm sorry, score. Technically, that's the variance of each score at each time point, right? Over here, for V, we only have 1 variable representing V, so we can only have 1 variance component for it, right? 1 residual variance. And so across the 2, we actually have a difference in the number of parameters. Over here we have 3 variance parameters, and over here we're only going to have 1 variance parameter. The way that we constrain these to be equivalent, and what you're getting over here, when it gives you the variance parameter for V, is just the mean variance parameter across time 1, time 2, and time 3. So we can constrain the variance parameters for time 1, time 2, and time 3 to be the mean variance parameter, and when you do that, you'll get the exact same, it's the exact same model. And we'll do it today just to see, so you guys can see what I'm talking about. But
yeah, question which can be like, I don't know, is it right or not? Like when we do like t-test or repeated measures ANOVA versus real ANOVA, so we have an autocorrelation between the times. So if we code them in the long format, we will get bias estimates, but here we are actually, this is actually a wide format, we're putting in the long format between LGCM and MLM, but still we are having the same, like, we don't get the wrong effects in MLM.
Correct. Yeah, so, wait, rephrase your question for me. I'm not sure if I grabbed it.
So there's an autocorrelation between the, like, time 1, time 2, and time 3 variables.
Yes.
And in LGCM that is taken care of, I think.
Say that again.
In LGCM it is taken care of, the autocorrelation between time 1, time 2, and time 3. Because they are autocorrelated, and do we model them in MLM as well? Like that?
Yes, so both M+ and almost every software out there will use an unstructured autocorrelation. So it is part of the modeling framework. You can go in and you can change that the type of autocorrelation to be like autoregressive or unstructured or any. There are a number of different types of structures that you can do. We're just gonna, for the time being, assume an unstructured autocorrelation matrix, serial autocorrelation matrix. But certainly there are ways. M plus is actually really. This is one of the issues that I hate with M plus is it's really hard to change the autocorrelation matrix. Though in the next version of M plus, they're supposed to be coming out with a command where you can just specify the autocorrelation matrix, and so you can specify it as like AR1 or something like that. Right now you can't. In Stata you can. Stata you can change it to any sort of thing. But you're right. It is like it's taken care of in latent growth curve modeling. You don't have to worry about the autocorrelation. It's actually set based on the time that you specify for each path, right? Which you don't get in multi-level modeling. But yep, that's absolutely right. Anyway, okay, let's keep moving. And as with latent growth curve modeling, we can recenter time. And as you recenter time, you will you can make your intercept. You can move your intercept around. Now, in mine here, I centered, or I called time 1, 2, 3. If we call time 1, 2, 3 in the multi-level model, that doesn't quite match up with what we have over here. Our slopes will be exactly the same, right? But our intercept won't. What's our intercept going to be? In the multi-level model, the way that I have it written up here versus over here.
So the average level across all times?
No, not quite.
Be the mean level at the first, at time 1, not at the origin, not at time 0.
It won't actually be the mean level at time 1. What would it be?
Would it just be the mean across people?
No. So what we're doing here, right, is we're plotting a slope that goes from 0, 1, 2. This is the latent growth curve. And let's say our slope is this, and it's 0.7, okay? In the multi-level, we still have a slope that goes like this, and it's 0.7. But now we're at 1, 2, 3. It's not going to give us this as an intercept, because technically this line is not really here, right? Our intercept is always at what? 0. So technically, this is where our intercept is going to be, and it's outside of our range of data. In the multi-level model, our intercept is going to be that. And so if we know that our intercept, actually, if we don't know what our intercept is, right? Let's say that it gives us our slope of 0.7, and we know that the mean level at time 1 is 0.9. What is our intercept going to be? 0.2. Perfect. That's exactly right, right? This should be 0.2, and that means this should also be 0.2, right? We can easily fix this by doing what? Centering at, you're absolutely right. It's not centering, but
We change our mean axis to 1, like at this.
Yes.
Shift axis to the right.
shift the axis to the right. And how do we do that? Over here, how do we do it over here?
We subtract the difference between 0 and 1 with all.
So we just subtract 1 from all values, right? Subtract 1 from all values. That moves our time 1 unit to the left. And that makes time 1 times 0, time 2, time 1, and time 3, time 2, right? And then you actually have the true intercept at time 1. Anthony, you look lost. Are you lost? All right. Let's do some, I will pull it up and we'll do it in Stata in a little bit so that you guys can see exactly what we're talking about. Yeah, go ahead.
Do you have to subtract it to make it 0, 1, 2, or can you keep it like this and just know that your intercept intercept value isn't your time one value.
Yeah, I mean, absolutely. If all you're interested in is slope, right? But if you want to know what your intercept is, or if you want to move that intercept around, then you can. I mean, let's say you want to know what the mean level is at the final time point, then what do?
You just find the slope, find the intercept.
You can just do the math. Yeah, sure. Yeah, you can do that. Unfortunately,
At like 1.3, like you have to
subtract 3, right? If you subtract 3, then what you actually are doing is you're making this, right? But you're extending this out to be -3, well, technically, -2, -1, 0, and your slope comes through here, and I suppose if we said that this was 0.2, that would be 0.9, and this would be 1.6, right? All we're doing is moving this piece of it, but we're not changing the slope at all. So then we'll know that like at the new zero, we're at 1.6 or whatever, right? Does that make sense? So yeah, it's just like what we were doing with latent growth curve modeling. You can move stuff around, and it's easy enough to just like say new time is this, or like you can change it to like time M3. I often will label them like time M3, which means time -3, or time M2, time -2, or something like that, right? But yeah, you can recenter stuff the exact same way as you've done it in latent growth curve modeling. And I feel like it's just kind of, it's smooth because it's in a regression framework. All of this stuff winds up being just a basic regression framework, and looks like a regression equation when we run it. But. All right, let's keep going. Within clusters, it's a little bit different. So within clusters is not a direct extension of latent growth curve modeling, though it can be a direct extension of latent growth curve modeling if you only model time as intercepts and you don't model time as slopes. And that means that you would always just use ones, right? So we're not looking across time anymore. We're looking at mean effects and mean associations. And that's exactly what the within cluster association is. It is mean relationships, right, at any given time point. We use this, I use this all the time when I'm looking at mood within subjects across days, right, and I'm less concerned with how much does your mood change across time, and more concerned with what is the relationship between your mood on a given day and craving on that day, or something like that, right? And so that's the type of stuff that we wind up modeling here. For those of you that do, like, I'm curious, if I try and think of IO stuff, sure, you can model like things within businesses, like attitudes within businesses, or attitudes within various offices within businesses. I don't know, offices. I am not an IO person. This has got to sound like blatantly obvious. I don't know what I'm talking about. but maybe maybe you're trying to like look at somebody help me out here. Give me something, IO folks.
That's good.
What's that?
Like daily work stress.
Daily work stress, predicting productivity, right? And so then you can model that like within person. Maybe you have like your individuals in a given company that are rating their daily work stress, and that you're using that to predict productivity. And somebody throw me some sort of between subject variable that we could look at here. Okay, so yeah, you guys both came up with the same thing. Yeah, so maybe we're interested in the relationship between individual differences in neuroticism or some sort of personality factor, and so we're looking at the relationship between daily work stress and productivity and the moderation effect by that person's neuroticism. And so for each of those, right, you're plotting a whole bunch of little regression lines for that person, a regression line for every single day, right? And then looking to see, like, does this relationship change as a function of that person's neuroticism? All right. So, as I said earlier, multi-level modeling is just really a special case of regression. The regression equations are broken up by level. I'm going to show you this in just a little bit. When you do a paper, when you write a paper using multi-level modeling, it's common to include the regression equations that you have in there. Regression equations can be broken up by level 1 equations and level 2 equations, or you can lump them all together in a single long regression equation, which I'll show you an example of here in just a second. So the parameters have both a random component and a fixed component. The fixed component is the mean effect across all people, and the random component is the extent to which that mean effect varies based on individual differences in person mean effects, right? Because each person has their own mean effect, and then across, and to be honest, if you do a 3-level model, right, then you have mean effects nested within mean effects. So does that make sense? You'll have a bunch of like average effects of a person, then you're going to have a bunch of average effects across persons, and then you're just going to have the overall average effect. If they vary a lot, then you'll see a random variance component. If they don't vary a lot, then the random variance component will be 0 or close to 0, or at least it will be non-significant. There's Rodenbush and yes, thank you. Is it Burke or Brick? I think it might be Brick. Anyway, they say that if your random variance has a p-value of less than 0.10 instead of 0.05, that it's okay to allow that component or that coefficient to vary randomly. I think they're just a little bit looser with the idea that some of these slopes might move around a little bit. They also have some odd things that I don't necessarily like. I mean, they are statisticians; they're the ones that know best. But for example, one of the things that they say is, regardless, you should always center everything. And we're going to talk about centering here in just a little bit. But they would say even gender should be centered. And I don't like the idea of centering gender or biological sex, because it just like loses meaning, right? Like you lose, I don't know. It doesn't affect the actual interactions, right? The statistical significance of a cross-level interaction if gender is centered versus if it's not. But it does affect the interpretation, because then it's weird. I mean, you wind up having to go back and set it at +1 or -1 or 0 or 1 anyway, right? So I don't understand the rationale of centering it, but that's what they suggest.
This random variance, residual variance.
What's that?
Each component is comprised of true variance and random variance. Is it residual variance? Or
It's yeah. So hold on, we're gonna get to that. It's on the next slide.
okay.
So let's just talk about it. So when it comes to coefficient estimation, we have randomly varying coefficients. So what I mean by true variance and random variance is, within a person, you are going to have true variance, right? At the lowest level, and that is the amount that a person, an individual, varies, right? Random variance is the difference between all of the slopes that partials out the individual level variance component. And so you wind up getting a regression equation that looks something like this: y equals I plus bx plus ri plus I don't know, rv, and this is actually at level 1. This is actually at level 2, right? It's the difference in individual level residuals minus total level residuals. It'll make a little bit more sense when we actually do this. When we do this, we have fixed coefficients that model only the true variance, right? And those fixed coefficients are the mean effect based on the level 1 variance, And then we have non-randomly varying coefficients that model true variance, that model only true variance, but predict this variance. You can predict this variance using some sort of higher order factor, right? And so when we do this, what we're saying is we are predicting, a good way to think about this is you can still have, let's say you have a slope between work stress and productivity, and you do not have significant random variance associated with that slope, right? You could still have true variance associated with that slope that can be explained by a between subject factor such as gender. This is why you can have a cross-level interaction with a level 1 slope, even if that level 1 slope doesn't have a significant variance component, significant random variance component. So we often think about having a significant random variance component means that we can look at an interaction. And if you'll hear people say this sometimes, just a second, you'll hear people say this sometimes, oh, there wasn't a significant random variance component, so we did not look at cross-level interaction. And that kind of makes sense in the context of latent growth curve modeling, right? Because if your slope doesn't vary significantly, then that means there's no way to explain variation in the slope via moderation. That is not necessarily true using multi-level modeling because of the two ways that we're parsing variance out, right? Individual level variance and random variance. And so you can still have a cross-level interaction that's helping to explain the individual level variance that is irrespective of significant random variance. The point of all of that is that you can enter cross-level interactions regardless of whether or not you have significant random variance components, right? Does that make sense? We're not just predicting slopes and intercepts anymore. It's predicting whether or not, or coming together to see if these coefficients can vary at the individual level. So, make sense? The take-home message is just that. You can have an interaction even if there's not a significant random variance component. Just remember that. Because you will hear people say that you can't, and the truth is you can. I have papers out there where we've found this, so you absolutely can have that. All right, what do these look like? Yeah, Richie, I'm sorry.
So, are you saying like if the ICC is not significant, then like people are saying you can't apply this or something?
I'm not saying that, but that's a good point, actually. People will say, so if your ICC is not significant, and you do a multi-level model, and if your ICC is not significant, you should not have a significant random variance component, right? And in that case, everything winds up being a level 2 model anyway, so it collapses to a basic regression analysis, and it doesn't matter. And so when people say, I just reviewed a paper where somebody made this case, like, oh, well, we didn't have significant. Actually, it was weird because they really just wanted to use multi-level modeling, and so they did it in the initial. They had 3 different models. In the first model, they said we had a significant amount of variance at the within subject level, and they showed their ICC, which was still pretty low. And then they said, so we were able to use multi-level modeling, and I thought, well, you can't anyway because it's just an extension of regression if the ICC is 0. But anyway, then they went on to the next one and showed that their ICC was 0, but to maintain consistency with the first analysis, they used multi-level modeling again. The truth is, if you multi-level modeling collapses to regular regression when the ICC is 0, so it doesn't matter. You can still do that, and this is maybe a better explanation of why you can still look at cross-level interactions, right? Yes, thank you. Did that make sense? Because as soon as I said it, as soon as you said that, then it started to make a little bit more sense. When there's no within subject variation, it still collapses to a regular regression analysis, in which case there can be significant basic interactions, right? Like just between subject interactions. So
I've read that when people find, I guess, non-significant ICCs or variance components, that they just don't use multi-level modeling. And then some articles I read suggest that, if the data are structured in a multi-level way, then you should always run multi-level modeling regardless of whether the ICC is significant or not. Like, how do you?
So I fall into that second group also. And the rationale, my rationale, is that even when there's not significant variance, you're violating something when it comes to regression and basic ANOVA. And what is the violation that you have there? Independence of observations. And with multi-level modeling, even without that, even with an ICC of 0 and no variation, you can still specify the fact that these residuals are autocorrelated in some way, even if it's completely unstructured, right? Multi-level modeling will take that into account, or you can regress those residuals onto the one before that, so you have like an autoregressive residual matrix. So absolutely, functionally they're going to be identical or nearly identical, right? But that might not always be the case. I don't know that I've ever run into it where it isn't the case, but also I don't know that I've ever run into it where an ICC is truly 0. So I think that's more of a theoretical issue than a true, like, data is so messy. I would be very surprised if somebody comes up with an ICC of 0 with no within subject variation or within level variation. But anyway, so when it comes to writing out your equations, you can write them in one of two ways. You can write them as a level 1 or level 2 models. So you see in this first one, we have this basic level 1 model. And that first one that I have posted there is a simple intercept only model, right? And so in our example that we were using for IO, our outcome was work stress. All that would be at level 1 is work stress, right? There would be no predictors at level 1. We would just be looking at work stress, and then we would be predicting work stress, mean levels of work stress by gender at level 2, right? And all this really is giving us is a t-test of work stress by gender that accounts for the fact that work stress is nested within individuals, right? If we move down to the next one, let's say now that we're predicting work stress from negative mood and positive mood, this should look a little bit more familiar. It kind of looks like what we were doing with latent growth curve modeling, right? Because now we have these coefficients. We have two slope coefficients, and we have an intercept coefficient. At the between subject level, we are predicting the level 1 slope of positive mood, the level 2 slope of positive mood, and the intercept by gender. And if any of those, so you see, I forget what the heck that word is, Y, it looks like Y01, Y11, Y21. If any of those are statistically significant, then we have what? What is that called? It's a cross-level interaction, right? Yeah. And that would be the fact that gender is moderating the slope, the B1J or the B2J. If the Y01 is statistically significant, what does that mean? I say Y, it's not really Y. What is that Greek letter? Anybody know? Is it gamma? Yeah, gamma. I think you're right. So if gamma 01 right here is statistically significant, what does that tell us? Yes, on the mean, on the intercept of the outcome, yeah, the outcome variable, right? It's the exact same thing that we have up here, right? And so this would say that there are gender differences in, if it's stress or work stress, we have gender differences in work stress. This, if this is a statistically significant effect, then we would say that there are gender differences on this slope, which is this slope right here, right? That means gender moderates the relationship between positive mood and work stress. And if this is statistically significant, then it's an effect on this slope, because notice we're predicting, right, the slope. We're predicting the slope. The slope is our outcome variable here, and so that would be there. You can put all of this into a single regression model that looks just like this. And note that this Y11 matches up to Y11 here, and Y21 matches up to Y21 here. Does that make sense? It's important when we start looking at this in the context of M+, because M+, we will have to break these things up by levels. All right. Did I already say this? Did it go the wrong way? No, it didn't. Okay, so like I was saying, this is just a special case of regression, and that's brought out by the fact that you can put all of these things into a single regression equation, right? It plots essentially a regression line for every single person in there, and for every single observation within person, collapses across all of those to give you a mean level at level 1 and a mean level at level 2, right? And at level 2, if we include so you can do something very interesting with this stuff. You can, let's say that we're just predicting positive mood or predicting work stress from positive mood. What we can do is we can take the average amount of positive mood across people and add that at level 2, right? And so if you have if your positive mood is 5 on Monday, 4 on Tuesday, 6 on Wednesday, and 5 again on Thursday, the average of those is 5. Your average level of positive mood is 5. That can be used as a between subjects variable, right? And so we can then center that positive mood. You would add 5 as a between subjects predictor, no different than gender or something like that, and then center across people, right? Everybody has some level. One person has 5, one person has 4, one person has 3. You center across people, and then you can have your own level of positive mood at on Tuesday versus Monday versus Wednesday. And in those cases, you're going to center across yourself, right? Which means that when you are at 5, your new value for positive mood for you as a person is 0. Yep. And so given the days that I said 5, 4, 6, 5, you would have 0, minus 1, plus 1, and 0 again, right? And so that's centered within yourself. At level 2, if you're controlling for your average level of positive mood relative to everyone else, what the level 1 effect becomes is a contextual effect, right? And that means for you, every time your mood is one value above your individual average, you see a gain of this in stress, right? Does that make sense? The contextual effect is saying controlling for your average level of mood when you move whatever that coefficient is, right? When you move one value above your average mood, you move X values based on the coefficient on your perceived stress. Does that make sense? Didn't make sense when I said it out loud. It made sense in my head, perfect sense in my head. We are going to do an example so I can show you guys exactly what I mean when we do the example. Yeah, Colleen.
Is there, you probably already said it, is there a name between, like for the one where it's just within yourself and then one compared to others? Is there like a label?
Oh, I think that, so I don't know about a true label, but I call it person level centering and grand mean centering, right? And so you can have a person level centered or within subject centering, between subject centering. When you have those two things that are the same variable centered different ways across levels, then it's called contextual effects, which is different than cross-level interactions, right? But like if you have like positive mood at level 1 centered within subject and at level 2 centered between subject, then you can then your level 1 effects are called contextual effects, right?
Why are they called contextual?
Because it's in the context of yourself, I guess. I don't know. To be perfectly honest, I don't know why.
Why wouldn't it still be
Just well, so it's not technically an interaction at that point, right? Like you're controlling for your individual level amounts, and so what you're saying is at level 1, when you deviate from your own individual level, because you're controlling for your mean amount, when you deviate from that mean amount, then you increase or decrease your y variable by whatever that coefficient is. And so I think it's just placing your variation within the context of yourself, of your average, and maybe that's why they call it that.
Why do we mean like if you do not do the mean center, you still get the effects. But
At-
it will not be two effects.
At level 2, like to be perfectly honest, you wouldn't have to center anything at level 2, and those contextual effects won't vary. They won't be any different because you're still controlling for your mean level, right? But it loses the value of where you're at with everybody else relative to everyone else. The level 2 value will change, right? At least the level 2 intercept will change. So.
And at level 1, if you do not center, then
Oh yeah, so at level 1, if you don't center, it can be very problematic. So the purpose of level 1 centering is to make sure that your ICC is accurate, the amount of variance that's parsed between level and within level. And it can have pretty significant effects on cross-level interactions. And we'll show that here in just a little bit. So, all right. So that is it as far as that goes. Let's take a little break. When we come back, we will dig into this data a little bit.